Hello, and welcome back to Boring Sleepy Scientist. Tonight, we're going on a journey through cosmic history. Imagine we're taking a slow, quiet walk through time, starting with the very first moments of the universe. We'll explore the life of a great cosmic detective, Edwin Hubble, and then gently ponder one of the universe's biggest mysteries, dark matter. Finally, we'll discover how some of the most powerful people in history, kings and popes, helped shape our view of the cosmos. Before we begin this soft exploration, I'd love to know where in the world you're listening from and what time it is where you are right now. Are you winding down under city lights or nestled somewhere quiet and dark? Perhaps with a cup of something warm. If you enjoy these sleepy explorations, I'd be so grateful if you gave the video a little like and tapped that subscribe button. It helps more boring, sleepy scientists like you find their way here, and it means I can keep making more of these soft starlit journeys for you. And now, I do hope this video isn't too interesting. Though if it does accidentally keep you awake, at least you'll come away knowing a bit more about the sleepy history of the universe. Not such a bad trade, really. Imagine, if you will, the universe as a grand, ancient book, its pages turning so slowly that their movement is almost imperceptible. Most tellings of this tale rush through the chapters, eager to get to the action, the explosions, the dramatic reveals. But here we shall linger, shall trace the delicate script of causality with the tip of our finger, pausing to feel the texture of nascent space, the warmth of the first stars, the cool, silent drift of cosmic dust. There is a profound beauty in this slowness, meditative quality that allows the true weight and wonder of existence to settle upon us, not as a burden, but as a comforting, all-encompassing presence. We're not here to rush to conclusions or to uncover thrilling new theories with bated breath. No, our purpose is simpler, deeper, to simply be with the universe, to listen to its ancient, slumbering heart. Our journey begins, as all good cosmic stories must, with the very first stirrings, the primordial whispers of the Big Bang itself. Even here, we won't plunge into a maelstrom of energy and chaos. Instead, we'll imagine it as the quietest of beginnings, a gentle exhalation that set into motion everything we know. Picture not a violent explosion, but an infinite, silent blossoming. An expansion so gradual from its own perspective that it felt like an eternal, tranquil sigh. We'll meander through the epoch of inflation, not as a period of dizzying expansion, but as a vast, serene landscape stretching out into infinity, cool and dark, yet pregnant with possibility. We'll watch, with eyes half closed, as the first particles condense from the energy, not as a sudden materialization, but as the slow, almost reluctant crystallization of something from nothing, like frost forming on a window pane. This is a history not of events, but of processes, subtle shifts, of gradual accretions, of the universe slowly, almost reluctantly coming into being. It's about the patient dance of gravity gathering gas into swirling nebulae, the long, slow burn of stars igniting in stellar nurseries, and the painstaking creation of elements within their fiery hearts. We'll witness these grand spectacles with the calm detachment of a stargazer observing the slow drift of constellations across the night sky, timeless, inevitable, and profoundly beautiful in their unhurried grace. Not nothing in the sense of an emptiness, but nothing in the sense of a fundamental, uncomplicated state. You are a loose, free-roaming proton, an electron, a whisper of a neutron, one of the lightest, most abundant things in the universe. There is no you in the way we understand it now. No body, no memory, no sense of self. Just existence. You are a part of the primordial fog, a thin, near-perfectly uniform soup of hydrogen and helium atoms, their nuclei and electrons uncoupled by the residual heat of the Big Bang. The universe is immense and quiet, and you are everywhere and nowhere at once. The light from the Big Bang's afterglow has long since faded, stretched out into the cool, dark microwave background that still bathes the cosmos. All around you is a profound, echoing silence, an immense blackness broken only by the faintest gravitational ripples and the scattered, lonely dance of your fellow particles. For millions upon millions of years, this is all there is. The cosmic dark ages stretch on, a quiet eternity of drift. You are not cold, for temperature is a measure of agitation, and there is almost no one to agitate. You are not lonely, for loneliness is a concept that requires companionship to be absent, and there is no one here to be missed. There is only the subtle, irresistible pull of gravity. It is the faintest of tugs, an almost imperceptible invitation to a dance that has not yet begun. You and your myriad identical siblings are all feeling it, a silent, mutual yearning to be closer. It is not a conscious desire, but a fundamental law of your being. You are drawn to the infinitesimal fluctuations in the cosmic density field, the places where a handful of your fellow atoms have already, by sheer random chance, gathered a little more closely than their neighbors. This is the great cosmic quietude, a period known as the Dark Ages, and it is a time of immense, unhurried significance. It is a time of pure potential. Think of it as the universe taking a long, deep breath before its first utterance. The tiny pockets of overdensity, the places where gravity's gentle whisper is ever so slightly louder, are the seeds of everything that will ever be. You, as a wandering atom, feel yourself drawn to one such pocket. The drift is slow, so incredibly slow. You might be moving at thousands of kilometers per second, but the universe is so vast and so empty that your journey feels like a standstill. Glide through the dark, your existence a simple, unthinking passage. Over eons, you feel the density around you gradually, minutely increase. The lonely drift becomes a gentle coalescence. You are no longer alone, but part of a gathering, an immense and silent cloud of matter that is slowly, patiently falling inward. This is not a dramatic collapse. There are no sudden events, no crashes, no collisions. This is a gentle, gravitational embrace. The cloud is a colossal, dark nebula, a vast reservoir of hydrogen and helium stretching light years across. It is still cold, so profoundly cold, but now you can feel the subtle pressure of other particles, their faint gravitational pull on your very being. You are part of a shared, quiet journey toward a common center. The energy that created you has long since dissipated, but the potential energy of your collective gravity is growing. As the cloud continues to shrink, its center becomes denser, and the temperature begins to rise. This is the universe's first stir of warmth, a shy internal glow that no one can yet see. You, as a lone proton, find yourself in the thick of it now. The space between you and your neighbors is shrinking. The occasional electron zips past, their speed an echo of the faint growing heat. The collective gravity of this immense cloud is immense, an inescapable hug. You and your fellow particles, drawn inexorably inward, begin to feel the pressure. It is a soft, increasing pressure, like being swaddled in countless layers of a heavy blanket. The random motion of the atoms, once a lonely dance, is now a frenzied jostling within a tightening sphere. You are part of an immense rotating disk, a protostar, a swirling cosmic embryo, its core steadily heating up under the immense weight of its own mass. The temperature at the center climbs. 100 Kelvin, 1000 Kelvin, 10,000 Kelvin, and still, nothing happens. This is the universe's patience made manifest. It waits. The clockwork of the cosmos is not a ticking bomb, but a slow-turning wheel. And for millennia upon millennia, the pressure builds, the heat intensifies. And the quiet promise of light remains just that, a promise. And then, a new feeling. Something is different. The jostling is no longer just random motion. There is a new kind of interaction, a different kind of collision. You are being nudged, pushed, and squeezed with a force you have never felt before. The pressure and temperature at the core are now so high, so profound, that something entirely new is possible. You are no longer just a proton drifting aimlessly. You are now part of a critical mass, a cosmic moment of truth. And then it happens. It is not a flash, or an explosion, or a sudden burst of glory. It is a quiet, profound, and utterly inevitable ignition. A proton-proton chain reaction begins. For you, as a proton, this means a union, a fusion, a gentle but unstoppable merging with another. You combine, you transform, you become something heavier. The process releases a tiny, powerful burst of energy, a photon, a messenger of this new cosmic reality. You are no longer just hydrogen. You are part of the new, heavier, and more complex helium. You have been transformed, and in your transformation you have created light. This is the birth of the first star. The light is born in the core, and it begins its long, slow journey outward. But this is not the light of a firework. This is the quiet, sustained brilliance of a nuclear furnace. A furnace so vast and so stable that it will burn for millions of years. This light, this first light, is the first thing in the universe to pierce the primordial darkness. It pushes outward against the immense gravitational pressure, creating a perfect, stable equilibrium. This new, warm, luminous thing, this star, is the universe's first conscious act of creation. And you, a former wandering proton, are now a part of it, a permanent member of its fiery, luminous heart. Your perspective has changed entirely. You are no longer a lonely drifter, but a part of a collective. You are part of a star. You feel its immense, patient energy, its steady, unwavering purpose. The star's gravity holds you in place, a force as profound as a parent's embrace. You are a hydrogen atom, and your purpose is to fuse, to release light, to become something more. The star is not just a ball of gas. It is a cosmic foundry, a forge where new elements will be hammered into existence over eons. You will be a part of this process, a silent, unseen participant in the creation of the building blocks of galaxies, planets, and eventually life. The photons you help create begin their slow, meandering escape from the star's core. They do not travel in a straight line. The core is so dense, so thick with jostling atoms and other photons, that each new photon is almost immediately absorbed by another particle, only to be re-emitted in a random direction. This is a cosmic game of pinball, a slow and patient shuffle. A single photon might be absorbed and re-emitted thousands, even millions of times. its journey outward a slow, drunken stumble through a sea of incandescent plasma. This is the radiative zone, and it is the second great crucible of your new home's journey, which would take a straight beam of light a mere second. Takes these photons in eternity, thousands, even hundreds of thousands of years. They are as patient as the gravity that birthed you, as unhurried as the universe's long night. Finally, after what feels like an infinite expanse of time, the photons reach the outer layers of the star, the convective zone. Here the material is less dense, and the heat is transferred not by slow-motion pinball, but by the slow, stately movement of the superheated gas itself. Bubbles of hot, glowing plasma rise slowly toward the surface, carrying the light and energy with them, while cooler plasma sinks down to be reheated. You are a part of this vast, gentle churning, a piece of a cosmic lava lamp. The surface of the star, its photosphere, is where these bubbles finally break, and the photons, at long last, are free. They stream out into the blackness, carrying your light, your energy, and the quiet message of your existence to the universe outside. From the outside, this first star is a quiet, brilliant point in a sea of black. Its light travels outward, a slow, patient beam in the darkness, reaching out to illuminate the immense nebulae from which it was born. The light you help create travels for years, illuminating the dark matter halos, the invisible structures that gravity has patiently woven. These first stars, these humble, quiet giants, are not alone. All across the dark universe, other pockets of matter are slowly, gently waking up. Other stars are being born, their light joining yours in a silent, shared illumination. These are the first glimmers of the universe's great wakefulness. They are the first beacons in the deep night, the first signs that the cosmos, for so long a domain of silence and emptiness, is beginning to fill itself with light. These first stars are unlike the ones we see today. They're massive, population 3 stars, hundreds of times the mass of our own sun. They live and die in a relative blink of an eye. Their lives are intense and short, their deaths spectacular. Their purpose is not to burn forever, but to create. They are the universe's first chefs, taking the simple ingredients of hydrogen and helium and cooking them into something richer. Inside their cores, you, as a proton, might be part of the fusion process that creates carbon, then nitrogen, then oxygen. You are a silent witness to this slow, deliberate alchemy, the birth of the very atoms that will one day form the stuff of planets, and mountains and oceans and living things. You are a part of a process so patient, so vast, and so profound that it seems to transcend time itself. Your home, this star, is destined for a violent, spectacular end. It will not fade away quietly. It will exhaust its hydrogen fuel, swell into a red giant, and then, in a final, brilliant act of self-sacrifice, it will explode as a supernova. In that moment, the immense pressures and temperatures will create even heavier elements, the ones that are the true building blocks of complexity. But that is a story for another time. For now, you are content to be here, in the heart of this ancient forge. You are a part of the light itself, a small, essential ingredient in the recipe for everything. You are a part of the quiet, beautiful unfolding of the universe's first grand dream. The first age of the cosmos is over, and the era of light has begun, all thanks to the slow, steady work of gravity and a sleepy ancient universe finally deciding to turn on the lights. And in this immense stillness, You, as a humble atom, are right at the heart of it all. What a peaceful, profound place to be. You are here, and you are. Edwin Powell Hubble was not, at the outset, destined for a life of looking up. Born in Marshfield, Missouri in 1889, he was a man of diverse talents and interests. He was a gifted athlete, a serious student, and a lover of literature. After his studies at the University of Chicago, he was awarded a Rhodes Scholarship and went to Oxford, where he studied law. It seemed he was set for a distinguished career as a lawyer, a profession that demands quick thinking and passionate debate. But even then, there was a quiet, internal pull. When he returned to the United States, he taught high school for a brief time. It was during this period that he made a decision that would change the course of human history. He returned to the University of Chicago, but this time, he pursued his quiet, persistent passion, astronomy. It wasn't in a hurry. He didn't shout about his ambitions. He simply, methodically, went back to school and earned his doctorate in the science of the stars. In his quiet way, he had already decided to trade the grand, noisy dramas of the courtroom for the silent, majestic theater of the cosmos, the quiet, cold labors of a mountaineer. Hubble's journey to Mount Wilson was not just a change of profession, it was a shift in lifestyle. The observatory was situated high on a cold, desolate mountaintop, a place of isolation and quiet solitude. The work itself was not glamorous. The 100-inch Hooker telescope, a massive and unyielding instrument of brass and glass, was a physical challenge to operate. The dome was unheated, and the nights were long and frigid, often lasting for 8 hours at a stretch. Hubble and his colleagues would work in heavy coats, sometimes with blankets wrapped around them, their breath fogging in the bitter air. The air was thin, and the physical exertion of moving the telescope and its heavy photographic plates was immense. This was not a pursuit for the impatient or the comfort-loving. It was a testament to the raw physical labor that underpinned so much scientific discovery. The process of taking a single exposure was slow and meticulous. Hubble would climb to a small cage at the focus of the telescope, a cramped and exposed position, and manually guide the instrument for hours, making minute adjustments to counteract the Earth's rotation. He was not a distant observer, but a physical participant in the act of gathering light, quiet vigil in the immense darkness. After the long exposure was complete, the photographic plate had to be carefully removed and developed in a dark room, a painstaking chemical process. The final product was a fragile glass plate, a silent record of the universe's distant light. Hubble's particular genius was not in some grand new theory, but in his unwavering patience with these glass plates. He would spend hours, days, even weeks, meticulously comparing one plate to another under a microscope. He would stare at the countless tiny pinpricks of light, his eyes a human instrument for a cosmic survey. It was in this quiet, tedious work that he would seek the elusive flicker of a variable star or the faint smudge of a distant galaxy. The great debate that raged in the astronomical community was about whether these fuzzy smudges were other galaxies. And Hubble's methodical approach was the only way to settle the argument. The scribe and the drifter, a collaborative patience. Hubble's work on measuring the distances to these galaxies required a partner, and his most significant collaboration was with Milton Humason. Humason was an unlikely partner, a man who had started his career at Mount Wilson as a mule driver, ferrying supplies up the steep mountain trails. He had a keen eye and an incredible patience for data, and over time, he taught himself the science of spectroscopy. While Hubble focused on measuring distance with Cepheids, Humason took on the equally tedious and crucial task of measuring the redshift of those same galaxies. The work was a quiet duet of patience. Humason would take hours-long exposures of a galaxy's light spectrum, capturing the faint smeared outlines of its chemical makeup. He would then meticulously measure the tiny shift in those lines toward the red end of the spectrum, a sign that the galaxy was moving away from us. It was a tedious, mind-numbing process. The galaxies were so faint and so distant that the spectroscopic lines were barely visible. It required an unwavering focus and a deep meditative calm to get the measurements right. As Humason gathered his redshift data, he would send the numbers down the mountain to Hubble. Hubble, in his own quiet way, would combine Humason's redshift numbers with his own distance measurements. He wasn't looking for a dramatic revelation. He was simply plotting the data on a graph. Distance on one axis, redshift, or recessional velocity. On the other, it was an act of pure, patient observation. It was in this patient plotting that the universe revealed its most profound secret. The data points formed a straight, clean line. The further away a galaxy was, the faster it was receding. There was no noise, no anomaly, just a perfect, beautiful, linear relationship. This simple, elegant line was the quiet, undeniable proof that the universe was not static. It was expanding. This was not a theory. It was an observation. It was so profound that it touched upon the great thinkers of the time. It was a quiet correction to the great mind of Albert Einstein, who had in his own theoretical work included a cosmological constant to ensure his equations described a static, unchanging universe, as was the prevailing wisdom. When Hubble's data was presented, Einstein himself would later refer to his addition of the constant as his biggest blunder, a testament to the power of observation over even the most elegant theory. Hubble, in his quiet way, had provided the factual refuel, patient observer. He never claimed to have discovered the expansion of the universe. He always credited the theoretical work of others, like Georges Lemaître, as the foundation for his observations. His triumph was the long, cold nights spent in the dome, the meticulous blinking of photographic plates, the quiet, collaborative work with his colleague. It was the simple, unhurried accumulation of data that led to the most powerful revelation of the 20th century. And as the universe continues its relentless, unhurried expansion, the story of its unfolding, the quiet labor of Vera Rubin. For a long time, we thought we had a decent grasp on what a galaxy was. It was a grand collection of stars, gas, and dust, all held together by the elegant, predictable pull of gravity. The stars spun around the galactic center, their orbits a cosmic waltz, governed by the total amount of matter, the visible matter within them. It was all very neat, very logical, and very sleepy. But a quiet and methodical astronomer named Vera Rubin in the 1960s and 70s would come to realize that the universe was not behaving quite as neatly as our models predicted. Vera Rubin was a scientist in the same mold as Hubble, patient, meticulous, and with an eye for subtle details. Hers was a story of quiet perseverance. In an era when the field of astronomy was still largely a men's club, she had to work harder, argue more gently, and simply prove her quiet competence through data. She spent her nights at the telescope, just as Hubble did, but she was looking at something different. She was studying the rotation of galaxies. She wanted to know how fast stars in the outer regions of a galaxy were moving. Our simple, intuitive understanding, based on the laws of gravity, as described by Isaac Newton, was that the outer stars should be moving more slowly. Think of our own solar system. Mercury, the closest planet to the Sun, zips around in a quick 88 days, while Neptune, far, far out, takes a stately 165 years. The same logic should apply to galaxies. The stars closer to the center, where the bulk of the visible mass is concentrated, should be moving faster than the stars on the outskirts, where the gravitational pull from the concentrated center should be much weaker. It was a simple, logical premise, a sleepy expectation. But when Vera Rubin and her colleague Kent Ford began to take their careful measurements, they found something profoundly odd. They looked at the Andromeda galaxy, the same one Hubble had patiently measured, and they looked at dozens of other galaxies, including the large spiral galaxy NGC 3115. They measured the speed of the stars at varying distances from the galactic center, using a technique called spectroscopy. The results were a puzzle. They plotted their data on a graph known as a galactic rotation curve. The curve, a line representing the speed of stars at various distances, should have sloped downwards at the edges, a gentle decline representing the decreasing pull of gravity. But it didn't. Instead, the line remained almost perfectly flat. This meant that the stars at the very edge of the galaxies were moving just as fast as the stars in the inner regions. They were not slowing down. The outer stars were zipping around their galactic centers at speeds that should have sent them flying off into the void. The galaxies were spinning so fast that based on all the light we could see, they should have been torn apart. It was a quiet, undramatic contradiction. It was a riddle. Something was wrong. Either our understanding of gravity was fundamentally flawed, or there was a vast amount of matter in the galaxies that we simply could not see. The invisible hug of a cosmic ghost. The most elegant and calming solution to this quiet puzzle was the latter. There must be something else out there. A vast amount of invisible, non-luminous matter. This is what we now call dark matter. It is a perfect name for a substance that does not emit, absorb, or reflect light. It is utterly, completely invisible, and yet its presence is felt everywhere. Imagine a galaxy. You can see its spiral arms, its bright glowing nucleus, and the starry rivers that flow through it. But now, with our new, sleepy understanding, you must picture this beautiful, visible structure being swaddled in a colossal, invisible halo. This halo of dark matter is much larger than the visible galaxy itself. It stretches far beyond the last star, a vast spherical cloud of unseen stuff. It is this immense gravitational hug that provides the extra pull, the missing gravity, that keeps those outer stars in their proper orbits. This isn't a theory born of imagination. It's a conclusion born of simple, patient arithmetic. The numbers simply do not add up without it. When you weigh a galaxy by its light, you get one number. When you weigh a galaxy by its motion, by the way its stars are spinning you, get a number that is sometimes 10 times larger. The visible matter is only about 15% of the total mass. The other 85% is this mysterious, invisible substance that we can only infer. It is a profound, humbling realization that for all our grand telescopes and our precise measurements, the vast majority of the universe is utterly opaque to us. We can't see it, but we can feel it. It is the silent shepherd that guides the galaxies, the ghost that gives them their stability. A deep and peaceful presence woven into the very fabric of the cosmos. More whispers from the unseen. The mystery of dark matter is not confined to the quiet, spinning galaxies. Its presence has been whispered in other places, in other grand cosmic scenes. The very structure of the universe itself hints at it. When we look at the largest scales, the great cosmic web of galaxies and clusters, we see that they are not randomly scattered. They are clustered into vast filamentary structures, with great voids of emptiness in between. Our simulations of how these structures would have formed based on the laws of gravity and the expansion of the universe simply do not work without a vast amount of dark matter. The visible galaxies are merely tracing out the invisible architecture of the dark matter. Filaments that hold the universe together. It's as if the cosmos is a great invisible skeleton, and the galaxies are just the luminous, glowing skin on its bones. Another clue, a truly stunning one, comes from a quiet cosmic traffic collision known as the Bullet Cluster. This is not a sudden crash, but a slow motion, gravitational meeting of two immense galaxy clusters. When these two clusters passed through each other, something beautiful and telling happened. We can observe the visible matter, which is mostly hot gas, using X-ray telescopes. This gas, being a fluid, collided and got tangled up in the middle of the cosmic smash-up, creating an immense plume of superheated plasma. But the stars and galaxies and the invisible dark matter simply passed right through each other like silent ghosts. Using gravitational lensing, the gentle bending of light from background objects, we were able to map where the total mass of the clusters was located. This technique, a quiet demonstration of Einstein's theory of general relativity, is like looking through a funhouse mirror. The light from distant galaxies behind the cluster is warped and distorted. By measuring the amount of this distortion, we can create a map of the mass that is doing the warping. And to our quiet surprise, the gravitational map of the mass did not line up with the location of the glowing gas. It lined up with the galaxies and the ghost dark matter that had passed through unhindered. It was a clear, undramatic separation of the visible and the invisible. A silent confirmation that this dark stuff was a real, physical part of the universe. The quiet search for an answer. So, what is this elusive substance? The answer is a great, unsolved riddle. For decades, our scientists have been on a quiet quest to find out. The leading theory is that it is made of some kind of exotic particle, something entirely new to our understanding of physics. The most popular candidate is a WIMP, or a weakly interacting massive particle. The name itself sounds a bit sleepy, doesn't it? A WIMP is a particle that doesn't feel the electromagnetic or strong nuclear forces, which is why it doesn't interact with light and passes right through regular matter. It only interacts through gravity and the weak nuclear force, making it profoundly difficult to detect. Labs around the world have built quiet, sensitive detectors deep underground. Trying to catch a single one of these shy particles as they pass through is a patient, painstaking effort to find a ghost, to catch a single, invisible whisper from the cosmos. Another older theory suggested that dark matter was simply a collection of faint, dim objects like brown dwarfs or black holes, things we couldn't see. These were called machos, or massive astrophysical compact halo objects. But our quiet, systematic surveys have largely ruled out this possibility. We just haven't found enough of them to account for all the missing mass. There is also the whisper of a more radical idea. Perhaps dark matter doesn't exist at all. Perhaps our understanding of gravity is wrong. This is the realm of MOND, or modified Newtonian dynamics, which proposes that gravity behaves differently on vast cosmic scales. While it can explain some of the galactic rotation curves, it struggles to explain the larger structures of the universe, like the cosmic web, and it has not yet been able to explain phenomena like the bullet cluster, where the gravitational map is clearly separate from the visible matter. It is a quiet alternative path, but for now, the evidence for dark matter as a substance is simply too compelling to ignore. And so, we are left with a quiet, profound riddle. The universe is full of something we cannot see. It's not a fantasy substance, but a necessary component of the cosmic ledger. It is a gentle reminder that for all of our triumphs and our hard-won knowledge, the universe is still full of immense, undramatic secrets. We can only see the faint, glowing wake of its presence, the ghost of its gravitational pull. We don't know what it's made of. It could be a new, fundamental particle, something that has no need for the interactions of light. It could be something far stranger, something we have not even dreamed of yet. The mystery is not a source of frustration, but of quiet awe. The universe is not just vast and expanding, it is also full of a deep and peaceful mystery. And as we sit here, contemplating this great dark puzzle, the universe continues its quiet, unhurried expansion, carried along by a substance we cannot see, in a story whose full text we have yet to read. The riddle is still out there, quietly. The quiet utility of the stars. Before telescopes and theories, the stars were a clock and a calendar. This was a form of knowledge that was far too important to be left to just anyone. It was the exclusive domain of rulers, priests, and the most learned scholars who were often patronized by the state. In ancient Mesopotamia, kings relied on priests to meticulously chart the movements of planets and stars, to predict omens and determine the right time for planting and harvest. In ancient China, the imperial astronomer was a high-ranking official whose primary duty was to maintain the calendar for the emperor. a direct link between the heavens and the earthly mandate to rule. The knowledge of the cosmos was not a source of philosophical contemplation, but a tool for statecraft, and its practitioners were supported by the highest levels of power. This tradition of patronage continued and flourished during the Islamic Golden Age. Caliphs and sultans, from Baghdad to Samarkand, saw the study of the stars as a noble pursuit. They were driven not only by a desire for accurate timekeeping for religious purposes, such as determining prayer times and the direction of Mecca, but also by a genuine scholarly curiosity. The Caliph Al-Amin of the Abbasid Caliphate founded the House of Wisdom in Baghdad in the 9th century, a vast library, an intellectual center where Greek and Persian texts on astronomy were translated, preserved, and expanded upon. He built the first large-scale observatories, not just for practical use but for the very purpose of quiet, meticulous observation to check and refine the models of Ptolemy. These were not the lonely, isolated endeavors of a single genius, but the immense state-funded projects of an intellectual empire. And they laid the groundwork for centuries of scientific progress. The caliphs, in their immense power and wealth, provided the time, the tools, and the quiet spaces for scholars to simply ... look up. The Pope and the perfect calendar. Perhaps one of the most ironic and enduring examples of astronomical patronage comes from a surprising source: the Church. The Church's interest in astronomy was, at its heart, a logistical one. By the 16th century, the Julian calendar was out of sync with the seasons. The date of Easter, the most important religious holiday, was slowly drifting. This was a quiet problem, but a persistent one, and it was a matter of great concern for the spiritual and political order of Europe. To solve this, Pope Gregory XIII enlisted the help of astronomers, primarily Jesuit scholars, and built the Tower of the Winds, an observatory and calendar-making machine at the Vatican. The work was not a flashy, revolutionary pursuit. It was a slow, technical process of observation and calculation to create a new, more accurate calendar. The result was the Gregorian calendar, which we still use today. The irony and the great quiet point of this patronage is that in their desire to create a perfect earthly calendar, the popes were funding the very science that would, just a few decades later, challenge the Church's geocentric worldview. This was a patronage of quiet, utilitarian need that unwittingly sowed the seeds of a revolution. It was a testament to how even the most conservative of institutions can, with enough patience and a single, practical problem, end up quietly advancing a cause they don't fully understand. The Aristocrat and his island for a particularly vivid example of what happens when immense wealth meets an obsessive passion for observation. We need to look no further than Tycho Brahe. Tycho was a Danish nobleman, a man of wealth, privilege, and a famously eccentric personality. He had a pet moose and a prosthetic nose made of metal after a duel. He was not a man of quiet, solitary contemplation in the modern sense. He was a showman, a grand figure who believed that the secrets of the universe would be revealed not through theoretical guesswork, but through sheer brute force data. His patron, the king, Frederick II of Denmark, was an aristocrat in the truest sense of the word. He was so impressed with Tycho's intellect and promised that he gave him an entire island, HVN, to build an observatory. This wasn't a small telescope on a mountaintop. This was a majestic, custom-built, state-of-the-art research complex called Uraniborg Castle of the Heavens. It was a palace for science, complete with a printing press, a chemistry lab, and a staff of apprentices. Here, with the king's immense financial backing, Tycho dedicated himself to the most tedious, time-consuming work imaginable. He and his assistants spent decades meticulously cataloging the positions of the stars and planets with unparalleled accuracy for their time. He had no telescope. He relied on giant sextants and other precise but manual instruments to measure tiny angles in the sky. It was a slow, methodical, and profoundly boring process, the very essence of the sleepy scientist's approach, but on a royal scale. The result of this lavish patronage was a goldmine of data. Tycho's observations, collected over years of relentless, patient work, were the most accurate ever recorded. They were not made to prove a theory. They were simply a quiet, deliberate accumulation of facts. And when Tycho died, his protege Johannes Kepler inherited this data. Tycho's life was a testament to the power of a king's checkbook. Without Frederick's immense patronage, Tycho's work would never have been possible, and the data that allowed Kepler to formulate his laws of planetary motion and thus set the stage for Newton's theory of gravity would have been lost. The Merchant's Need and the First Royal Observatory. The royal patronage of astronomy was not just about intellectual curiosity or personal glory. It was often a matter of practical economic necessity. This brings us to King Charles II of England and his desire to solve the longitude problem. The 17th century, ships at sea could determine their latitude with a simple sextant, but calculating their longitude, their east-west position, was a matter of guesswork. This led to countless shipwrecks, a significant loss of life, and a massive economic burden on the burgeoning British Empire. The solution, it was thought, lay in the stars. If a sailor could carry a perfect clock and a perfect set of celestial tables, they could use the position of the stars to find their longitude. And so, in a fit of pragmatic royal thinking, King Charles II, in 1675, founded the Royal Observatory at Greenwich. His motivation was not an abstract love of the cosmos, but the simple, unromantic, and utterly vital need to solve a maritime problem. He appointed John Flumstead as the first Astronomer Royal, with a single, clear, and immensely tedious mission: to apply himself with the most exact care and diligence to the rectifying the tables of the motions of the heavens and the places of the fixed stars, in order to find out the so much desired longitude of places. Flamsteed's job, and that of the Royal Observatory for centuries, was to create a precise map of the stars, a celestial atlas that would be as reliable as a compass. This was the patronage of commerce, of empire, and of a quiet, relentless desire for a practical solution. The Greenwich Observatory, a direct result of royal patronage, would go on to shape not just astronomy, but global time itself, as the prime meridian was set there. The aristocratic patronage of science? From the caliph's libraries to the king's observatories, was a slow, sometimes clumsy, and often accidental vehicle for cosmic discovery. These were not the lonely late-night discoveries of an individual, but the massive public works of an era. They were flawed, of course, driven by ego and political necessity, but they were also a testament to a deep underlying value placed on the quiet, methodical study of the cosmos. The aristocrats created the platforms, and the scientists, in their own patient way, used those platforms to peer deeper into the dark. And as the modern era would shift from private patrons to public grants, the fundamental dynamic would remain the same. The quiet work of observation, funded by larger forces, continues. The journey is now complete. Our long, slow walk through the sleepy history of the universe and its quiet observers has come to its gentle end. Please, do not stand up. Remain seated, or perhaps lie back, and let the quiet weight of what we have contemplated settle upon you. We began with the profound, impersonal calm of the cosmos itself, and we end with a quiet understanding of our own small but beautiful place within it. We started our story not with a bang, but with a whisper, the soft exhalation of the Big Bang, followed by an endless, dark quiet. We imagined ourselves as a single, unthinking atom, a fundamental particle adrift in a silent, unimaginably vast cosmic sea. For millions of years, there was only the slow, inexorable pull of gravity, a force so gentle and so patient that its work was almost imperceptible. We were part of the primordial fog that, over eons, began to coalesce, too slowly, reluctantly, fall in on itself. This was the universe's own first act of sleepwalking, a dreaming state that patiently gathered the ingredients for its first great act of creation. And then we were there, in the heart of that celestial forge, helping to ignite the first massive, quiet giants, the population 3 stars. We were part of the light itself, a small piece of the silent, luminous awakening of the cosmos. This was a story not of human triumph, but of universal process, a reminder that the great unfolding of existence does not need our observation to proceed. It simply is. And yet, to fully appreciate that impersonal grandeur, our story had to narrow its focus, to descend from the cosmic to the human. We turned our gaze from the slow, unthinking evolution of matter to the conscious, quiet labor of a single man. We contemplated the patient, persistent life of Edwin Hubble, a scientist who chose a life of cold, solitary drudgery on a mountaintop over the public clamor of a courtroom. His was a testament to the power of pure, unhurried observation. The discovery that the universe was expanding was not a sudden epiphany, but a triumph of patience, of long, frozen nights at the telescope, of meticulously blinking plates, of a gentle, methodical partnership with his assistant, Milton Humason. Hubble's triumph was in proving that the universe's story was not just a static backdrop, but an active, unfolding narrative. He revealed the great, unhurried motion that had been there all along, a motion that we had simply been too unobservant to notice. No, his quiet work transformed our understanding of everything, all because he simply chose to sit still and watch. But as with all knowledge, Hubble's triumph was not an end, but a beginning. Our contemplation of the expanding universe led us to a new, deeper, and more humbling mystery, the great, undramatic riddle of dark matter. We followed in the quiet footsteps of Vera Rubin, who, with her own methodical patience, found that the galaxies were spinning too fast to be held together by the gravity of their visible parts alone. We were forced to confront the serene and unsettling truth that the universe is made of something we cannot see. We imagined the silent gravitational embrace of a vast, invisible halo, a cosmic ghost that holds the galaxies together. We contemplated the whispers of its existence in the quiet, gravitational lensing of background galaxies, and in the ghostly, unhindered passage of the bullet cluster. This was not a problem to be solved with urgency, but a profound and humbling mystery to be quietly accepted. After all our hard-won discoveries, it turns out we can only perceive a small fraction of what is actually there. The universe, in its deep cosmic wisdom, holds most of its secrets close to its heart, inviting us not to frantic action, but to quiet awe. And finally, we took a contemplative step back from the solitary scientists to look at the larger, more social story of their work. We explored the role of the aristocrats of science, the kings, popes, and nobles who, in their desire for power, commerce, or even simple timekeeping, inadvertently shaped the course of cosmic discovery. We saw the quiet, scholarly patience of the Islamic caliphates, the practical, PayPal need for a new calendar, and the grand, lavish patronage of Tycho Brahe by a king who saw scientific precision as a form of royal grandeur. This was the great, quiet irony of our story. While science today often feels like a lonely pursuit, for centuries, it was a public spectacle, a grand, expensive project funded by the powerful. The quiet, personal discoveries of a Hubble or a Rubin were only possible because of the long and often messy history of patronage that came before them. The grand, unhurried sweep of cosmic history was only charted on this little planet because the very human drives of power and prestige, in their own quiet way, deemed it worthy of support. And so, we are left with a single, unifying reflection. The story of the universe and our place in it is a story of slowness, of patience, and of a gentle, persistent unfolding. It is a story of an immense cosmos that does not rush, a lonely scientist who patiently watches, of an unsolvable mystery that quietly waits, and of a human history that, in its own slow and often accidental way, has learned to value the pursuit of truth. Our existence is not a frantic dash, but a long, quiet drift. We are but a small part of a story that began in a whisper and continues to unfold with the same unhurried grace. The greatest lesson is perhaps the simplest: to simply sit still, to listen to the quiet, to feel the profound peace of a cosmos that is in no hurry to reveal its secrets. It will unfold in its own time. We have only to be here, to watch, to wonder, and to rest in the tranquil knowledge that we are a part of it all. This is the whole of our story, and now it is. So, let your eyes close if they have not already. Feel the gentle, gravitational pull of the Earth as it holds you in its quiet embrace. Just as the galaxies are held in the silent grasp of dark matter, let your breathing slow, mirroring the unhurried expansion of space itself. And with that, I bid you a very good night and a very good rest. This is the boring, sleepy scientist, signing off.